Hello everyone, my name is Zhaozhuo. I'm from Rice University. I'm a CS PhD under the supervision of Professor Anshumali Srivastava. Today I'm going to present a novel deep learning method beyond convolution for seismic data ingestion. This is a collaboration with Shell, and this is the first paper, if I remember correct, this is the first paper in the AI conference from the energy industry. So this may be cliche. So this is for machine learning people, not for energy people. Just a recap of seismic inversion. Basically, we have source, we have receivers. We need to collect signals from the bottom of the ocean and do seismic inversion. A more close look on the data, because we have different locations, different source location, different receiver location, and then we collect different signals. And for our area of interest, we select the corresponding traces and do seismic inversion. So a more clear look at the data, we can say that it is highly irregular. Of course, the shape is varying. And also, we have 5D information, which is the source location, receiver location, and the trace signals. Traditional seismic inversion workflow takes time, and we are seeking for data-driven method, basically directly generate subsurface model from the raw data of seismic. Here is the traditional pipeline. So we are regarding the seismic data as images, and then we apply convolutions. This is a typical idea from the computer vision industry with the success in image recognition, object detection, and so on. However, we find a significant problem. I think doing convolution in seismic imaging is suboptimal. First, it should the seismic image is not actually an image. It's a composition of different trace signals, different 1D signals with locations. And also, if we directly apply convolutions on these 5D data, it will take a lot of time and consume a lot of memory. And I'm not sure if what is happening in the industry, but from our survey, there's no like real data exploration in the seismic related papers. People are playing with simulations. There's also a well-known SegSaw data set, which will be shown later. Our main argument is like raw seismic data is not an image and should not be processed as images. So in return, we are taking analogy from seismic inversion to a language modeling task, which is machine translation. So in the next step, we'll see what is their common, what are there in common, and how to solve seismic inversion as we solve natural language processing, and we propose SSD, set embedding based seismic data ingestion model. So this is also very important in the major challenge of seismic inversion is we have terabytes of raw data, we have a gigabyte size of velocity model, and it is impossible to put them all into computers and do seismic inversion. This is what we can borrow from NLP. So NLP, of course, if we do machine translation, you are transferring a Spanish book to an English book. You cannot feed all the book text into computer. So instead, they decompose the task. Like given the context of English, we want to predict the corresponding Spanish. So it is kind of like a breaking the big task into a small task. And this is the current paradigm for language modeling. And this is also the way that BERT learns the sentence embedding and word embedding. Similarly, we can do the same thing. So for a given velocity cube down in the ocean, we can collect the corresponding seismic traces and then perform inversion. So we call this an accelerated task. It's an analogy to the language modeling where you want to predict the word given the context word. Another thing is like we need to handle the irregular data because as we discussed before, seismic is not image, like you cannot just simply do interpolation or denoising or smoothing. So instead, we're talking about, this is a recap of word-to-vec. Basically, it's a full MLP model. Given every context word, we first embed them, and then we do aggregation on the embedding, and finally, we want to predict the target word. So similarly here, given the separate location-aware traces, we want to predict the final velocity cube. And of course, we have advantages over traditional method. First, we are saving the time for the pre-processing, such as we do not require the raw data to be an image, and we did not apply convolution, which is more efficient. Also, our proposal contains the auxiliary task, which can decompose the whole inversion problem into small problem, which will benefit the parallelization in training and inference. So to summarize, our proposal is just like a seismic ingestion problem, but we transform into an NLP formulation, and then we propose a set embedding to handle this problem. Okay, so finally, we are presenting the results. It is a Gulf of Mexico dataset, thanks to the Shell and TGS for providing the data. So on the left is our prediction, and the right is the ground truth. So we can see we can have a good capture of the salt body. And this is from the raw knife merge seismic traces. And the whole area is like 2 kilometers by 6 kilometers. We can see a small shot. So this is a small data. So we are training on other data set, and this is our prediction area. And the way we do this is that we decompose the final prediction cube into small cubes, and then collect the corresponding seismic traces and training a neural network to do that. So if we find a cube so there's a problem that the cube may have different depths. So for more deeper velocity cube, we are collecting more wider in the surface signal so that we can have more accurate prediction. So this is a network architecture, basically given trace data, source location, and receiver location. We first embed them separately by first we apply MLP to have trace embedding, then we have a location embedding, then we basically concatenating them, and then apply our MLP to do feature aggregation. Finally, we are taking the average over different trace embeddings and for the final velocity cube prediction. We are training a 1 billion parameter network, and by utilizing the full 5D information. And this is the small visualization result. So we can see that we have a very good prediction on a small cube, but there's maybe some problem in the actual characterization of the shape of a salt body. But we are showing that it is possible to directly generate a subsurface model directly from raw unfiltered seismic traces. And of course, if we are submitting to ML conference, we need to have some benchmark. We need to compare with UNet. This is a SegSalt dataset. It's a classical seismic inversion dataset. And we actually compare two versions of our method. The first version is like the full, if we use all the traces. Another version is like, what if we just subsample half of the traces? Does the model still have the same results or better results? So here is our visualization. We find out if we subsample them, it's not actually hurt too much. And this is our simulation result. We just follow the standard in a geophysics paper. Yes, so a little more detail about the subsampling. So because now we are not doing convolution, we are just doing embedding on separate traces. So it is totally doable to subsample the traces and maintain a faster in training and both inference. So so another interesting phenomenon we observe is like if we random subsample 50% or 80% of traces every time, it actually prevents overfitting. So it's like we are fitting the neural network with different examples, but they're sampled from same distributions every time. So in this case, we can have better performance in a way that we can prevent overfitting. So of course, there's a standard metric like L1 in the test and PSNR, SSIM. We are finding that we are better in terms of evaluation matrix, and also in the dataset that we previously introduced in the shell dataset, the UNet is infeasible due to the computational resources. So we are not just outperforming UNet and transformers in standard benchmark, but we can also do on some data set that UNet is unachievable. So in summary, like SSD is an efficient raw seismic data ingestion method, and it can achieve promising results with imaging and convolution. So to summary, this is the first work from the energy industry to the NeurIPS. We are facing a lot of questions, including we are also under an ethics review because the reviewer says like, oh, you are consuming the oil and gas or something. But finally, we are presenting a poster in the NeurIPS, and we are getting good results and good feedbacks. Feel free to scan the code and check out our paper. Thanks.
Questions? That was super quick. Questions? No questions.
Yeah, very interesting talk. So you compare this one with the NLP. So in NLP, there's actually embedding language model and then the fine-tuning part, right? So this one, I'm wondering, if you train the model, can people just leverage your model and do the fine-tuning for their task?
Yeah, so that's a very good question. So actually, so the SSD model is comparing with the pre-training phase of the language model. Basically, we want to learn good trace embeddings. Of course, we are seeking opportunities to have downstream tasks, which is basically not just do seismic inversion, but do other tasks like a density prediction or something. So we are open to different downstream applications, and we really hope that this can be start for like we have a general model for seismic inversion, then for other tasks, we can fine-tune the task. Yeah.
Okay, Felix Herman, Georgia Tech. It's an intriguing talk, but I have a little bit difficulty understanding how you can assume locality, right? Because variations in the velocity model talk to everywhere in the data. So if the velocity model is relatively simple, then that's a very good assumption, and basically a lot of trace-based old seismic data processing techniques were based on that. But if you have a salt body, as you have, then there's a much more non-local phenomenon. So I was wondering whether you have some intuition why what you presented still works in that case.
Yeah, so we also take that into consideration. Actually, the hardest part of our model is learning the salt body. So, so the way the trick we apply, I have to be honest, is like first we need to emphasize like on the shape. For example, the loss function, we need to have a very strong L1, so that we can have a good capture of salt body. Also, for the trace, so there's in language modeling, there's also some similar method that can handle it. For example, if you apply attention, but the attention has a problem, like if you apply attention, finally all the trace embedding will look the same. So how to handle that? Basically, you need to have a residual block. Basically, you have to emphasize if you are making good prediction on the salt body, you need to encourage them. If you are doing something wrong, you need to penalize them. So we also add some penalty in the training of the model.